Here's problem 31-1. A coil is wrapped with 300 turns of wire on the perimeter of a circular frame, radius of 8 centimeters. Each turn has the same area equal to that of the frame. A uniform magnetic field is turned on perpendicular to the plane of the coil. This field changes at a constant rate of 20 to 80 millitesla in a time of 20 milliseconds. What is the magnitude of the induced EMF in the coil at the instant the magnetic field has a magnitude of 50 millitesla? Alright, so we have a circular coil. Radius of the coil is given as 8 centimeters, 0.08 meters. So we can figure out the area of this coil. That's going to be pi r squared. Pi times 0.08 squared gives us 0.020 meters squared. Okay, so that's the area of this coil. And in fact, we have 300 coils. So we have 300 turns of coil like this. So the number of turns we have is 300. And we have a magnetic field that's perpendicular to the plane of this coil. So let's just imagine that our magnetic field is going into the board. And we turn it on, and our initial magnetic field is 20 millitesla, and our final magnetic field is 80 millitesla. So our change in magnetic field is our final minus our initial, which would be 60 millitesla. Alright, so if we were to turn this magnetic field on, there would be an induced EMF to oppose the change in flux that is increasing into the page. And so the magnitude of that induced voltage or EMF would be equal to the number of turns times the magnitude of the change in flux over the change in time. In this case, the flux is going to be equal to the field times the area, and the area is not changing. So this would be the number of turns times the area times the change in the magnetic field over the change in time, at least the magnitude of that. So we can calculate this voltage. That is going to be the number of turns, 300, times the area, 0.02, times the change in magnetic field, 60 millitesla, and that's going to happen in 20 milliseconds. So we can get rid of the 10 to the minus 3 on both. And so we have, let's see, 300 times 0.02 will give us 6 times 60 divided by 20, it would be 3. So this would be 18 volts. So we will induce 18 volts in this coil, and that will be a constant voltage for the time that the B field is changing. So even though we wanted to find the magnetic field at the point where EMF at the point where the magnetic field is 50 millitesla, which would be in the middle of that changing of that range, this voltage will be the same over that whole range. So it doesn't really matter that we selected that point in particular. The EMF will be 18 volts at that point.